Hey, so rotation. What do I want to say about that? Yeah. What is rotational motion? How does it compare to translational motion? Well, we can define. hmm, Sorry, I'm just looking for my teacup here. Oh, here we go. Let's use my chair over here as an example to illustrate the two types of motion: translational versus rotational. Now, when I say translational, I just simply mean uh, linear motion. Linear motion, okay. And I need to pin one of these things. So there you go. I try to make it a little bit closer to us. Okay. Okay. Check out this chair. Now, when something translates without rotation, then over a period of time, every particle or part of that system traverses the same distance or travels the same distance in the same amount of time. Every part. So if I'm moving along, at some constant speed, this thing is just, let me show this thing. So this thing is just rolling along, right? So a displacement is going to be a certain distance that it covers. So like say this particle here moves, a certain distance in a certain amount of time. But if I go to any other part of the chair, say something apart over here on the ledge on the armrest, it also moved that same distance, same displacement in the same amount of time. In fact, same direction, everything. But now, if I were to swivel this thing so that it's spinning around on its axis, like so, well, obviously that's not true, right? Because if I'm at a point at the axis, that axis is not translating. A point on the axis doesn't translate at all. It just spins around, rotates around, or revolves, I guess. But if I'm on, say, some part here on the shoulder of the rest of the chair, that's mapping out a circle in the horizontal plane, right? Well, let's see, because that wasn't on the thing, but let's say a point right here. So that's mapping out a circle, in the horizontal plane that maybe is that big, right? So that distance that it travels is the circumference of that circle. But if I'm on a ledge right here and I spin the thing around, well, that's going to map out a wider circle. So whereas one object particle is moving around maybe like this, or well, I guess actually if it's here, then it would have been something like that. But this guy is a little bit wider, so it's mapping out a circle like that. So that's a characteristic of rotational motion that not all the particles, they travel different distances as the rotation occurs. And if it's a rigid body, which we assume that is rigid, meaning that all of the parts of the system maintain the same distance from one another, at all times. So a rigid body, we say it undergoes rotational motion when um, every particle of the object travels in a circle, except of course the ones at the on the axis of rotation. And the axis of rotation, we have to define that, is the straight line through that extends through the center of the circle described by all of the particles experiencing that motion. So that's kind of a lot, but let's go ahead and write both of these definitions down. So translational motion versus rotation. Rotation. Rotation one. So translation or translational motion. Each particle of the rigid body of a rigid body has the same displacement in the same time interval. Okay. So each object, each differential element of the rigid body that is experiencing the translational motion experiences the same displacement in the same time interval. That's translation. Now, what about rotation? Well, we just said that um, rotation or rotational motion is such that each differential element or each element of the rigid body um, travels in a circle centered about the axis, travels in a circle. So each element of the rigid body, with the exception of those on the except or C and except. think so. All right. Yeah, it's gotta be right. Except elements on the axis of rotation. Define that in one. So each element of the rigid body, except elements on the axis of rotation, travel in a circle of, so the axis of rotation is the line through the center of all circles mapped out by all elements. So that's another thing. The axis of rotation, abbreviated AOR, is the line through the center of all circles mapped out by all elements. And one other thing I wanted to say. The circles have varying radii depending on the distance. Well, the distance from the axis of rotation determines the radius of curvature, or the radius of the circle. So, couple 3 points here. Yeah. A couple things there with the rotational motion. So one, the rotational motion is defined by the fact that each element of the rigid body maps out a circle as it moves. The radius of the circle is defined by the distance that the object or the element is away from the axis of rotation. And the axis of rotation is a line that goes to the center of all circles mapped out by all particles. That is to say that all of the circles are geocentric. with respect to one another. Maybe we should write that too. Oh, geocentric. Maybe that's not no. Are all circles are centered. All circles have a common central. All circles have a common axis of rotation. Put it that way. That's what I want to say. So scratch that statement about being geocentric. Geo means Earth, so that doesn't make sense as applied to this scenario. Well, not necessarily. Um, geocentric orbits all have all geocentric orbits would also be the same. They would map out a circle and there have a common radius. Uh, but the point I'm making is so a geocentric orbit, if you don't know, is when something is orbiting right above you and it doesn't move. So because the Earth is rotating, the reason that the thing doesn't move is because its orbital revolution is the same period as the Earth. So it looks like it stays in place relative to particular points on the Earth. So that's that's called a geocentric orbit. Um, yeah. So technically, that's not applicable to what I was doing here in general. Uh, Not always, but in this case, whatever. You get what I'm sorry, I'm a little bit tired today. So, yeah, that's it. So that's, I guess, a qualitative introduction to rotational motion versus translational. And over the chapter, we're going to do a couple things. We're going to define the quantities associated with rotational motion, just like we did with kinematics. We first started by defining displacement, and then we did velocity, average velocity, acceleration, average acceleration, and then looked at the equations of motion. Here, we're going to do something similar, but we also, once we get these rotational displacement, rotational velocity, rotational acceleration, they are actually related to translational properties. For example, let's say that I had picked out three particles on my chair there and they were rotating. So let's say that we're looking from the top down so that we see the circles that they're mapping out and we can see them moving in their planes. I'm going to draw a picture that represents three different particles moving, about some in concentric circles about some rotational path. So one path will have an inner radius like this, then another guy is like this, right? And then another guy is like this. Now these particles, particle 1, particle 2, and particle 3. So what we're saying is that, let's say their motion is counterclockwise, so they're going around, all of them, like that. Now we're going to define what it means to have an angular displacement, an angular velocity, and so on. But we already know that these, even though they're moving in a circle, we can still define a translational uh, quantities associated with them. If we say that the velocity is tangent to the path at every point, which we do, we know that that tangential, we'll now call it a tangential velocity. So v sub t, or v tangential, that's the same thing as the linear velocity, right? That was also what we called, you know, just v, I guess linear, with we usually put a coordinate on it, like vx or something like that. Hope you can see that. But, and there is going to be a radial velocity that we'll define here momentarily that is related to this. So basically what I'm trying to say is that we have to, once we figure out what the rotational quantities are and define them, we then have to describe them in relation to the linear quantities. In other words, how does the rotational velocity compare to the linear velocity that you can describe as being the tangent to that path. Same thing with acceleration and rotational acceleration and all the quantities. So that's something that's necessary. Okay. Well, the first one is kind of easy because you already know it. You just have been looking at it from a very different perspective. What am I saying? Okay, well, let's take another example of a rotating object. Let's take like let's say that I have a dot, on my ruler here. And I take my ruler and I pin it to the board, just like here, like maybe it's pinned here, it's mapping out the object. And I spin the thing around. Oops. Well, let me hit that. So let me come over here a little bit. Oh, I'm sorry. I spin around. So it's going to spin, right? If I had an object here, it's going to map out a circle, right, moving around. Okay. Now, if I were to define an axis, am I hoping this camera to turn around? Put the camera in the middle. Just block the board. Yeah, yeah, okay. Just trying out a new camera position here. By the way, you tell me, is that better? Can you see the board a little bit better? I think the camera is a little bit more forward. Is that a little bit better than normal or no? You want to give me some feedback on that? It is better? Wonderful. Thank you. Cool. Awesome. All right. It's clear than before. Okay. All right. Yeah, let's keep it like that. I mean, I got a new phone too, so what do they call it? The iPhone 15 titanium or something, whatever the nickname is. So the camera is better, but that also might be affecting. I got it about a week ago, but whatever. Yeah. What was I doing? Um, oh yeah. So we still can define a coordinate axis, right? We can still say that because we have to have some, when you start to measure displacement, whether linear or angular or whatever, you got to have a reference point. And so I could come here and make an axis, just a standard axis with, I could call the vertical, well, in this plane, I'll call the vertical y, or in this two-dimensional plane, and the horizontal x. And z is going to come out of the board. It's going to come out this way. Okay. So I guess I should put that over here because we need to say something about that here momentarily. So the z-axis, well, you know, I could draw it three-dimensionally, but I want to make it so that it's rotating in the plane. So if that's so, yeah. So just note that z-axis, positive z-axis would have to be coming out of the board in order for this to be a appropriate orthogonal coordinate system. Now, again, let's say that I come over here and I take my oscillator and I pin it at the origin and I start to whip it around like this. Oops, a problem too, but let's say I start here and I spin it. So what happens is it opens up relative to the x-axis. In fact, it opens up what I say in a counterclockwise direction relative to the x-axis. It is spinning around. Now, I'm going to take a snapshot of that particle, of that object. And, the whole thing is rotating, but let's just say that this is some sort of massless rigid string or whatever. And my mass is at the end of that, and it's rotating out here, right? So that's my object, mass 1. Maybe it was on the end of a string or something. I don't know, whatever. Now, the distance that the ruler represents is the radius, is what we defined previously as r, the position vector. And it points from the origin to the place where the object is, exists in space. Okay. So that's R. Now, theta is going to be the angle that defines, um, I guess that's technically the radial distance from the origin, defines that radial distance from the origin relative to the x-axis. So theta is this guy. And I also have one other thing. I also have something called the arc length, the actual length, the path length that this thing is mapping out. If it's in a circle, it goes through the x-axis horizontally. And then, so that I'll call it S. It's actually, I could call it, yeah, I'll call it S since I gave X the X, the X, so yeah, just call it S. And so it gives rise to what something you're familiar with, which is the arc length formula. However, I'm not going to write it as the arc length formula because uh, that's not really truly what it is. That's not a concept within itself, the arc length formula. In fact, the arc length formula comes out of this concept, which is the definition of an angle. This is where an angle is actually defined. And it is a unitless number because it's defined in terms of the ratio of the arc length versus the radius. That is to say that the angular position, theta, is defined as 3 = the arc length divided by the radius of curvature. And in this case, I made it simple. I made it a circular arc, but it doesn't have to be a circle. It can be any curve. Whatever the radius of curvature is at that point, that's going to define something called basically an angular, like S over R is the angular displacement of that thing relative to some, original position. Yeah. Now, if it is moving along a circle, then R is constant and doesn't change. And so therefore the displacement then is going to be equal to a delta. So like, in other words, delta theta, which you could define it as that. Here I'm assuming that theta is 0, but delta theta is going to, well, space over here. So bring it back over here, let's say. Delta theta is equal to delta S over R. Or you could, flip these around and solve for S, and this leads to the arc length formula S equals R theta, and maybe more appropriately, this could be written as delta S is equal to R delta theta, and as the limit goes to 0, then you could say a ds, a differential path length, is equal to R times a differential angular displacement. Okay. But ultimately, this is the definition. This is a definition. So this is where the arc length formula comes from. It comes out of a manipulation of the definition of the angular position vector. Right? It's not a vector. It's just a position. And you can see that one thing we could say about theta is this is why it's a unitless number. But we have to call the angle something, so we just call them degrees. But a degree is not a unit, technically speaking. So, we say, for example, that one revolution in a circle is equal to 2 pi radians. Is so we say that what am I saying? Oh yeah, it's the circumference. One revolution is defined as circumference. Well, the length of one revolution. the length of one revolution is defined as circumference. Um, so yeah, that's how you get one revolution equals 2 pi radians because um, one revolution, right? Theta is going to be. What am I trying to do here? So yeah, if I use that formula, then you get in one revolution is the circumference, um, 2 pi. Yeah, so the circumference C over R is equal to 2 pi times the radius, which is the definition of circumference over R. So that establishes that in one revolution, since the R's cancel, the angular displacement is 2 pi. Now pi is 3.14. It just I think Pythagoras knows supposed to figure this out. And so they just gave it a name, radians, as I don't know, an abbreviated rad. So that's where we start with the angular displacement. That's 2 pi radians. And so any other angles, that's 300. That's so basically the conversion relationship is that 2 pi radians or rad equals 360 degrees. And so then we can just figure out, everything else from there. A half, a circle is pi radians, which is 180 degrees. A quarter is um, 1/4 of 2 pi, which is going to be pi over 2. And that equals 90 degrees. But it's established essentially by the unit circle or by the circle. Yeah. Okay. And also the other thing about angular displacement, which is different than the translational position vector, is that angular displacement is cyclical. That's cyclic or cyclical. Both of them are correct terms. And one's an adverb, one's an adjective, I think. But uh, so we can say angular position is cyclic. Position is cyclic. And I think the name describes itself. It means cyclic, means cycle. So what it's saying is that as you move in a circle, there are repetitive occurrences of position. So whatever the position is, so if I started at the origin, right, and I went around pi radians, sorry, 2 pi radians, which we can see is the angular displacement that we just showed is the angular displacement for one revolution. That if I go around one revolution, when I'm at the end of that position, I'm going to be at the same physical position that I was when I started relative to the origin. And if I go around if I go around 5 pi radians, sorry, if I go around 10 pi radians, which is 5 times, then I'm going to be back in the same position. 1, 2, 3, 4, 5. So any whole number increment of any degree puts you back in the same physical position. So in other words, the distance you travel, which will be 2 pi r, but your displacement is always going to be 0 whenever you go around one revolution, because displacement technically is just the final position minus the initial position. So if your final position is the same as the initial position, as you know, your displacement is always going to be 0. So with this scenario here, theta equals 2 pi radians for one revolution, cyclic means that we can write something called a recursion relationship. Again, these words are very well named. Relationship, because a recursion relationship is a relationship that defines something that's recurring over and over again. So theta then is equal to n times 2 pi, where n is equal to any whole number integer, 0, 1, 2, 3. Um, and defining theta cyclic, that means that theta is equal to theta plus 2n pi, the physical position is. Yeah, so these represent the same angular position. Angular position? Yeah, I guess. Yeah. Same angular positions. I call this theta m. Yes. Actually, this is theta m. So then I guess I don't need this. This is all right. I got to mix up the notes. Okay. Actually, this doesn't have to be whole integrals. I mean, I don't even think I need that actually. I guess that's what's throwing me off a little bit because it doesn't really matter. Yeah, I guess we do want to hold this. We could talk about, yeah, okay, sure. I don't know, I'm overthinking it probably. Um, yeah, okay, so that's it. That's this angular displacement and angular position. Now, yeah. Mm. So how do we get speed? We just simply take the derivative of the angular position. And the symbol that we use for that is omega. Oh, omega. By the way, theta is spelled as th theta, theta. And um, yeah, we take the derivative. So angular speed or velocity. Well, that's one thing I didn't say about it. I had to say it, but I'll go back and say it again. But we will say it in conjunction with speed. So I just take the derivative of this guy, right? 3 and 4. So if we have and then take the limit as delta t goes to 0. Well, what is that? That's a derivative. So ds dt is going to be the derivative of the right side. So r d theta, all that's dt. Technically, it's a chain rule, but r is constant, so it would give you 0. In other words, what we're really saying is that we're taking the derivative of r times theta, right? But when you do the product rule, the first term, theta dr dt, is 0. So then the second term you're left with, which is just, and so then we define this ds dt as, yeah, as the linear. Actually, this also gives a relationship of the linear velocity, as I was saying before, to the angular. So you have v, which is the translational, or vt, tangential velocity, is equal to r times d theta dt. And I guess I really should have started there, but whatever. So then so this thing is defined as the angular speed. So we get omega, and your book might say something like omega z, and what that is they're setting up an axis like this where, and that's the thing I didn't say, is that position is a vector. So what should be its direction, x, y, or z? Well, it doesn't make sense to say that it has a position in the xy plane, in the plane in which it's rotating, because it's rotating. So at every point, it pretty much has a combination of, its position is defined as having components in both x and y. But the one thing that doesn't change with respect to position is the axis of rotation about which it is rotating. And I set this up such that the thing is rotating, the axis of rotation is actually the z-axis. So that would define the rotation. In other words, if I just could pick the thing rotation up, if I had the thing rotating around, kind of like a pixie stick like that, right? Then however the direction that I'm pointing, my axis is pointing, the rotation is perpendicular to that. So just by knowing the direction of the axis of rotation, you know how the plane in which the rotation is happening. So for that reason, people define the axis along the axis of rotation, the direction along the axis of rotation, as the direction that defines that motion. So some books, when they're teaching this, they emphasize this by putting a little z on the coordinates to let you know that they're setting up everything so that it's rotating about the positive or negative z-axis. So you might see that in your reading. So like a omega z here, the definition then is just this term here, d theta dt, or d theta z dt. So it's the time rate of change of this angular position as the rotation occurs. And that's it. That's the definition of angular velocity, is this guy, equation 7. And it makes sense, right? Linear position is the derivative of position, linear position. Angular velocity is the derivative of angular position. Right? Angular velocity. Now I could give it a vector here, so then this would be a vector as well, meaning that the direction along the z-axis. Now, also implicit in this formula is a relationship between the tangential and the linear, and these first two is kind of easy. They're like right in there, so kind of, well, definitely for this guy, this is the linear position and this is angular. So the relationship between linear and angular is inherently there in the definition. Right? Or the arc length formula shows that explicitly, although that's not really. The definition is the ratio of the positions, or the radius versus the arc length. Now, I could then emphasize this relationship in equation 7 by writing it like this, that the linear velocity or tangential velocity, either one, is equal to r times omega, where omega is the angular velocity, or omega z. We're kind of seeing a pattern here when we're looking at these relationships. We have the linear quantity is equal to the radius times the rotational quantity. Same thing here. It's kind of a symmetry there. And of course, the speed is just the magnitude of the velocity. So we have to, it would be defined in the same way, just like with linear motion. Meaning that, the speed is the magnitude of the velocity. So what I just taught you, sorry, I'm kind of tired and sit down. What I've just taught you um, defines the what am I saying? Ah, let's see. I just lost my train of thought. Oh, let's look at both of these examples here, using my illustration as a guide to this next point. Mm. So we've established two kinematic quantities, new ones. Well, not necessarily new, but redefined in the context of rotation here, at least for the arc length formula. And define theta to be the rotational equivalent to r. It's related to r through the arc length formula. Now, the velocity for something like this, like in this particular problem here, the angular velocity is defined as coming out of the board. And the tangential velocity, again, to reiterate, it would be tangent to that path. So it would be like here. Okay. VT. And omega, well, what people say is that omega then would actually point out of the board for rotation in the counterclockwise direction. Now, the symbols that we use for in and out, I think I've done this before, but maybe not. So vector notation. A vector pointing directly into a board, in, is represented by a circle with a cross hatch. It really represents the back of an arrow going in. What you would see is the feathers on the back. And for something coming out of the board, you would just see the point. So this represents a vector coming out, and this is a vector coming in. I had used that early to represent the z-axis, saying that it's an axis pointing out. So I should have probably put it right here at the, in fact, I should, because it's with the axis. So I could just put it like right here. And so it represents an axis, coming out. And what we're saying then, when you see these two notations, the angular velocity is also pointing out parallel to z. So you can clearly see that there with that type of notation. Now, we have to introduce something called the right-hand rule at this point. You've probably heard this before, and there's several different ways that you can use the right-hand rule. I've got three that I teach. Two of them are really right-brain and more intuitive with regard to the physical phenomena itself. The more formal definition is, we won't get to that when we do until we get to torque, because even though there are relationships that define them with respect to these quantities. In fact, I shouldn't write this. This is actually the magnitude. I shouldn't put a vector symbol there because both of those are vectors. And as it turns out, they actually have a relationship. The vector representations of those vectors, of those quantities, have a cross product relationship, which we don't really deal with at this level. So I'll just write this definition as a vector, and I'll leave that relationship up there um, as it is. Same thing here as well for all of them. They have different. There's other things we can say about them with higher mathematics, but we won't because it's just not done at this level. We present to you the magnitude, so just assume that these things are the magnitudes of these versions of these vectors. Now, um, the fact that the rotation is happening in the xy plane absolutely dictates that the angular speed will be either, or angular velocity will be either along the y, along the z-axis, the positive z-axis, or the negative z-axis. But what dictates which one? Well, it's the orientation of motion. And you can use the right hand, the curl point method of the right hand rule, to determine what direction the rotation is. Take your right hand, curl your fingers in the direction of the rotation. So in this case, curl would be in the counterclockwise direction. So curling around counterclockwise gives, and you make a fist then as you're doing that, and then point your thumb. Your thumb points in the direction that defines that rotation. So positive z, if this thing is moving in a counterclockwise orientation, and for circular movement, I'm going to use the word from now on, orientation. So orientation means something is rotating, and what is it? Clockwise or counterclockwise? Either one of those two answers. Direction implies a vector quantity pointing, or the direction of a vector quantity, not a rotation. So the orientation of this rotational motion is counterclockwise. The direction of the rotational motion is the positive z-axis. Due to the right-hand rule, curl point. I'll write that down in a minute. If the object were rotating in the clockwise direction, curl. Remember, don't switch hands. It's a running joke in physics and in E&M. Mostly in E&M, though. But when you start seeing people doing the right hand rule and they're at a test and they're just going at it and they start working with their left hand, right? They're already dead in the water, so to speak, made a mistake. So it's the right hand rule. Why is it the right hand? It's completely arbitrary. I think it goes back to this archaic stuff about left-handed people were supposed, left-handedness, back in the Middle Ages was supposed to be of the devil or something. I don't know. So, the mathematicians, they were working back then. So I guess they said, well, I better use my right hand or I might get burned at the stake or something. I don't know. But it doesn't really matter. You can use your left hand and just throw in a negative sign. So whatever. Uh, it's really interesting. I like to kind of put that in there because it's kind of an interesting thing. Like, why? Why do we make it a right hand world? I don't know. But it doesn't matter. Just know what you're doing if you decide to do that. But yeah, you have to throw in a negative sign if you use your left hand. But use the right hand. So yeah. So if I were to rotate in the clockwise direction, curl point, my thumb is pointing in the negative z axis. So that would be omega then and theta or delta theta would be defined as in the positive in the negative z direction for clockwise rotation. Yeah, that's it. And of course, now that we have this definition for omega, we just need to take another derivative, the second derivative of theta of s, excuse me, or the first derivative of omega gives you the angular acceleration. Want to do that? Yeah, just keep it rolling here, I guess. Well, I just finished this. I'll come back over here. What time does it break? Oh man, I didn't get much sleep last night. That must be why I'm fading. Stayed up late. I've been, as you can see, didn't say anything about that. You can see I'm kind of doing some renovations still. Well, you can't really see from this too close. Maybe the other camera. Yeah, you can see from this camera that I kind of moved my bookshelf and stuff. I've been doing some fall cleaning, carpets, and a little touch-up painting on this board. This board looks a mess because I have my ink spots all over it. Cleared them out and trying to repost my little stuff here. So I was up late working on that Sunday night. Yes, I was. Let me change this out. What am I doing? Yeah, we're going to take the derivative again. So starting from equation 7 here. All right. Yeah, I want to do it from that point. So if I take derivative of omega z, which is the same as the second derivative of theta, then I have, yeah, then I can define that as alpha z, the acceleration, the rotational acceleration. And um, yeah, uh, I think that's it. Yeah, this is the definition. Yeah. Angular acceleration. We also define it as being perpendicular to the plane in which the motion occurs. So yeah, just it. Yeah. Okay. So 10 minutes before the break. And I'm probably gonna go a little bit because I started 10 minutes late, didn't I? Or 7 minutes late. Yeah, let me just go ahead and knock this out. I can knock out the equations of motion real quick. Now that I have this guy. Yeah, so that's it. That's the definition of angular position, velocity, and acceleration. Now, let's start. We're going to look at two types of motion. Just like before, we can have constant motion or accelerated motion. Two types of rotational motion, constant or accelerated. Two types of rotational motion. Uniform, which means that the direction or well, I guess constant. Let's say constant. Yeah, so constant motion, which implies that alpha z is equal to 0, so that v initial equals, well, omega initial equals omega final, and omega z, right? And accelerated motion, in which case the alpha z is non-zero. Let's first derive the equation of motion for constant motion, and we'll do it just like we did before. Well, actually, before I didn't use calculus, did I? I went back and derived it from basic, and then I did calculus later on. Oh, well, I did, but I'm not sure if I posted that yet. I was supposed to post the drag stuff, which I did, but I don't know if I posted it. I think I posted a portion of it, and it's in there where I use the calculus to derive the equation of motion really fast. If not, I've done it, but I'll go back and see if I posted it. But I did do all that. But here we'll start with this equation here, right? Yeah, and then we do separation of variables and integrate. So yeah, so equations of motion. So constant motion, rotational motion, that is. So starting with, so if it's constant, then that means omega z is a constant. So omega z is defined as d theta dt. Okay. Well, one of the things that we like to do is we like to get everything. We can use something called separation of variables. This is basically a differential equation that we have to solve. So the thing that's varying is the theta is varying with respect to time. And so we want to know how it varies. What is the functional form? How can we can predict the position of the particle at some later time? Well, with a differential equation, the idea is you solve it, and that solution will tell you the functional form such that if you put in the independent variable, time, it'll tell you where the dependent variable is or how it has changed relative to that independent variable. So that the simplest technique to do that is something called separation of variables. In fact, when I do this, it's not even going to look like I'm solving a differential equation. It just looks like common sense. But that is what it is. That's what's happening. So separation of variables, separation. I had a biology teacher, Mrs. Carter. Oh my gosh, she was so good. Separation of variables. She said she was a stickler on everything. 10th grade. She said, there is a rat in separation, so do not misspell it. Funny the things you remember from teachers that you have. I was 15 years old, so that was literally almost 45, 40, 44 years ago. Wow. I can literally remember her in class at the board saying that. I don't know. It's a kind of a selective memory. I think it's called something. There's a name for it. I have don't have a very good memory, but I have that kind of memory. So like if there's a song or a movie, I can remember like the when it came out because I can remember the emotional things around it a lot of times. I remember when I was in the movie watching it, you know, just arbitrary, very arbitrary things. Um, yeah, so there's a rat in separation. Um, Separation of variables. This the thing about and I didn't say that here, did I? Yeah, I didn't specify it. So theta has units of radians, but I told you that's not a unit. In terms of the system international, that's not a unit. So technically omega, it's just it has units of 1/seconds. In fact, from a different perspective, we wouldn't even consider it a velocity. We would consider it a frequency, an angular frequency. In fact, I have to define it. I think I've already defined it, but I'll define it here again. We've defined frequency. Frequency is 1/period. But what is angular frequency? Well, you can probably take your hint from this stuff because frequency is considered kind of a, it's not really linear, but it's associated with linear motion. Angular frequency obviously is associated with angular motion. But if you look at the this trend here, linear quantity versus rotational quantity times r, linear quantity proportional to, well, wherever it was here, linear quantity proportional to radial quantity, and the proportionality constant is the radius. You might expect something like that with the relationship between angular frequency and or something like it. Anyway, we'll say that in a minute. But um, the point that immediate point is that the units of angular velocity is 1/seconds, not radians over seconds, but radians is just a number. So 1/seconds is, or hertz really is the unit for angular frequency. And in separation of variables, the idea is to separate the differential equation so that all types of quantity of one type are on one side and all of the other type are on the other side. So when I multiply through this equation by dt, I'm going to have omega z dt equals d theta of t. And because omega has units of just seconds or 1/seconds, time stuff, and there's nothing, so that's it, they're separated. When they're separated, you can integrate. Now technically it's like an indefinite integral and you have to do boundary value conditions and find the limits. I'm going to do a quick shortcut here just for the purpose of teaching, and the shortcut is that I'm going to integrate with the definite integral going from t equals 0 to t and going from theta equals theta naught, the initial theta, to theta of t, the position at some other angle position at some other time. And so this just integrates to delta t, right? So that'll be delta t. So omega z times t, let's keep these equations going. So 10, 11, 12. And then over here, I just have delta theta, right? Theta of t minus theta naught. And if I solve that for um, position, theta t, well, look at what I have. Theta of t is equal to theta naught plus omega z times t, which is what you expect, right? Because that mimics the linear equation, the comparable linear equation for constant velocity or average velocity. We did it two ways back then. So that mimics this equation, that that x of t is equal to x naught plus vx times t. So that's the first equation of motion for rotational motion. is the position equation. This guy, analogous to the position equation in one dimension. I think we're at oh, it's 2:30. I'm gonna go a little bit over. Well, you know what, I can do it. Yeah, it does. I can do that later. So yeah, I might go a little bit 10 minutes over just to get that 10 minutes in. But let's take a break right now since it's 2:30 or yeah, 2:30. I need to take a little bit, maybe 20 minutes. So, but I would encourage you, see if you can do this. Like you can take a break, come back, because what we're going to do is now I'm going to, what are we going to do? We got to get the other equation. So there, what we do is, yeah, I just start from the definition of angular velocity, which I erased. It was here. No, yeah. Well, this guy. D omega dt is equal to alpha z. And see if you can do the same thing. You do separation of variables, and it's going to give you the velocity equation. Um, yeah. And then you can yeah, with the velocity equation, you can then take the derivative again to get the or not take the derivative, but integrate again. Use the definition of of, of this guy in that next equation and integrate again, and it gives you the position with respect to time for accelerated motion. So this is constant motion, but for accelerated motion, obviously accelerated motion because you have this guy. You can so there's only one equation for constant motion. That's it. But we had four equations. That's what I'm trying to say. This was constant motion. So the next thing we're going to do is accelerated motion. Sorry, I just start back at that. So accelerated motion. Um, we have four equations of motion. So I was saying two types of motion: constant motion, accelerated motion. So this is constant. This is the only equation associated with constant motion. Accelerated motion, we have four equations, basic equations. So accelerated. I just thought of something. It is ERAT and accelerated. Using, and I do mean it in the sense of that kind of southern drawl thing that people do. I think it'll start with Tyler Perry's character or something. That language. Uh, yeah, I can't remember it. Whatever, I think you know what I'm talking about. So there's a rat in separation, there's ERAT in acceleration. I'm sorry, I need to take a break. I'm just getting silly. But yeah, so you start here, you do the same thing, it gives you the velocity equation. Then you put in this definition into that result, integrate again, separation of error, it gives you the position equation. And then with those two position equations, you'll see that they'll be analogous to what we have with linear motion. You can solve those simultaneously algebraically, eliminating t and then eliminating alpha to get the velocity squared equation and then the average velocity equation. So that'll be the four equations of motion for accelerated motion. I'll do that when we come back from break, but you can get a jump on it and remind yourself of what we did. Or you can go back and look at your notes from linear motion stuff from early on and just follow along with that. All right, let's take 20. All right, I think we're back. Yeah. So I wanted to finish deriving these equations of motion for your rotation. So to get the first equation, the velocity equation for accelerated motion, we start with this guy. I'll start over here. Again, we're going to separate the variables. We're assuming we have constant acceleration, so separating. Remember, this is acceleration is radians per second squared. And so when I multiply through by dt, I have radians per second squared times dt seconds, which is just radians per second. And that's the same as omega. So on one side of the equation, I would have omega or d omega. On the other side, I'm going to have alpha z dt. So that has units of angular velocity, radians per second. This has units of angular velocity, the total radians per second. So the variables are separated, and then we can kind of do a cheat integration where we just put in some definite integral, definite limit. So omega naught to omega t. And of course, this guy is 0 to t. And that's outside the integration because it's constant. And that's an alpha, not a 2. So this integrates to delta omega, right? So we get omega t minus omega naught, and then that's equal to alpha z times t. Then solving for omega t, we have omega t is equal to omega naught plus alpha z times t. Okay. Sorry about that. Yeah, so here we go. We got this in. That's you can see that's the velocity equation. Or constant acceleration. That was quick, and now we can do it again by putting in the definition for theta or omega, which is d theta dt. So we start again. D theta of t dt is equal to omega naught plus alpha z times t. Multiplied through by dt of d theta. T is equal to omega naught dt plus alpha z dt, and then just integrate again. So integrating this guy from theta naught to theta of t, this guy 0 to t. Oh, sorry, there's a t in there. Sorry, I left that off. That's a t and dt. Of course, alpha z is still constant, but the t is, it's a variable, so no, that goes from 0 to t. Oh, so yeah, we integrate. Left side is just delta theta, so we have theta of t minus theta naught. delta theta. Here, oh, this integrates to t, and so we have equals theta naught times t, and then plus, so t integrates to t squared over 2, so that's where you get the 1/2 alpha z t squared. And then to get the final version that we like, we just take the initial position over on the other side. And finally, we have theta of t equals theta naught plus omega naught t plus 1/2 alpha z t squared. Actually, you know what? It's gonna bring that over here so you can see it very clearly. Uh, theta of t equals theta naught plus omega z times t plus 1/2 alpha z times t squared. Yeah. So those are the first two equations of motion, equation 21, equation 17. And we can then, we have the two other equations again, we solve them simultaneously. So the way we do that is we solve equation 17 for t and substitute it into here, and we get the velocity squared equation. So I'll just remind you that I've done it before with the linear motion. I'm not gonna, I'll let you do that derivation on your own, but we'll just remind you here. So solving, so basically eliminating t, eliminating, eliminating t between 17 and 21, we get omega squared equals omega naught squared plus 2 times alpha z times delta theta. Theta, I just put delta theta in here, and then eliminating alpha between those two equations. Alpha z between 17 and 21. We will get I'm sorry. Yeah, what? I'm just tough day still on task. Yeah, what am I doing? Yeah, so then you get the what I call the average velocity equation. And it says delta theta is equal to 1/2 omega naught plus omega z um, times t. And so that's it. That's going to be the four equations for accelerated motion. In terms of rotation, equations 17, 21, 22, and 23. Oh, goodness. Yeah, yeah, cool. So now we've got, you know, basically we have got four types of, well, five really now, motion we considered in this class. We did the way that I broke it down from my problem solving technique. Oh, there's motion in X and Y, general motion in X and Y. And of course, there's general meaning you have constant motion and accelerated motion along the X and Y directions. Then you have free fall motion, which that's what we call when we're just moving, just dropping an object. So that's three. Then parabolic motion is the combination of constant motion in the X direction and free fall motion. We had a set of equations for that. Then we kind of threw in, I guess, a special case of rotational motion, which was centripetal motion, centripetal acceleration. And so I still classify that. Let's just go ahead and put that down as a type. And so that's what, six? Oh, that's six. And let's just go ahead and make this a category, just general rotational motion. Now we'll call seven. So that's seven types of categories of motion that we have studied in this class. There's one more that we will study at the end of the whatever chapter is oscillations, and that I would call eight. So that's basically how I kind of think of physics in my mind, is that we have these different classes of motion that have certain properties that we like to group together and call that a classification of motion. So yeah, we're moving along here. Rotational and translational quantities, yeah. The section on that. Well, I've kind of done some of that already, but I have a section where I kind of do that, and then we get into conservation of energy and then property of inertia. Yeah. All righty. We're chopping along here. I'm really enjoying this class this semester for some reason. I don't know. Um, you all are pretty conscientious students, and I appreciate that very much. Although I wish people could come to class, but I'm glad that you all do consistently. But no, I get it. I mean, I guess having a conversation with a colleague recently, it is so incredible how fast our society is evolving. It's just so incredible. Um, yeah, and so this is part of the evolutionary process, is being able to provide quality education in the way that we're doing here. But I also think it's going to help in another way. I think it's the world is moving faster, and this actually is kind of helping to cover more material. I think in the same amount of time, it's just a much more efficient process with getting. But it takes a long time to kind of develop these classes. appropriately with these learning management systems. But um, yeah, it's coming along. I don't know if I had the conversation with this class, but I tell it every now and then. My first job out of college was an engineering plant job with the Bell companies. I'm from South Carolina, so out here it's like Pacific Bell, I think, and South. But in South, it was Southern Bell at that time. This is back in the late '80s, mid '80s actually. And I I was got a really good job, with engineering, you know, in the phone service. It's not really engineering; it's like phone engineering, which whatever they called it engineering, but it's like cookbook engineering at best. But anyway, it was a good job. It was a fun job, and I was young, I had a lot of fun. But the first day on the job, it all the senior level engineers were so excited because in the meeting, the weekly meeting that started on a Thursday, they were all some of them had already started putting in this new cable that had a really fancy name called Slick 66. Slick 66 was like the first or second generation optical fiber, which was replacing the cables, the copper cables. They had already either started or just about were to finish putting the cables across the Atlantic Ocean to Europe. And so they were ready to start the infrastructure of that process, transitional process, all over the North American continent and basically the States. And I kid you not, this is the words that were in the meeting and my first thought. Now, remember, I graduated from college in 1986, undergrad, and the PC came out in 1984. So it came out when I was a junior. Right, it was the first rollout of Apple company. You know how they roll. I mean, they just had a rollout a couple at the beginning of the month of whatever new things they come up. They do it. But the very first one, I was there. I was in college. It was the Mac, the Apple PC, and we got a couple at our school. I think or something or no, somebody got some. I guess some. Yeah, they had them, and the only thing that you could do with them is basically word process. Like there weren't any apps. There was none of that. It was just basic, and that's the Apple. The other PC was there was MS DOS, so you had to actually know MS DOS to actually do the thing. Anyway, so 2 years later, I'm uh, in fact, just a quick story. I took my first programming class before the PC came out when I was I think it was the second semester, maybe sophomore year. I can't remember. I had to take computer science. And the language we used, they taught us was Fortran. I mean, completely, don't laugh. But we were still we had to write our programs and then we had to get a punch card and take it to the mainframe on campus and give them the punch cards to run the program. That's, you know, so when I was a freshman in college, that was computer science. Scroll forward, basically 50, 40, what was it? I was 18 at the time, so 40 years. I'm teaching, I mean, oh, and the other thing they said, so in the meeting, everybody was really excited, because it's optical fiber, it's technology, and mind you, now there were no cell phones back then. The cell phone that was out at the time was that first generation, the big thing that you see. That was the only cell phones that were around, and only major company. I think my father had one because he was working for the state. He had like one of those. In fact, he'd gotten the first. He'd gotten the first generation, and I was in 10th grade is when they actually came out, the first actual cell phone. And I'm talking that big old thing with go Google it, and you'll see when they first did the commercial or whatever, or the guy who made it or whatever. So basically, those were still the cell phone. They were a little bit smaller than that first one because it was 5 years later, but that's. And so we're in the meeting, and the head engineer says, "Well, yeah, we got to really get this thing going. It's going to be a whatever year process to kind of get most of the major wires, major cables, replaced all throughout, like in our region, which is the Southeast, is about 4 or 5 states. But we're doing it all over the country because we're preparing, get this, we're preparing for this thing called the World Wide Web, where you'll be able to just store information on computers. That was the name. And it'll be just really versatile. It's not just information. You can do things like ultimately you might be able to you might be able to buy and sell things, and might even be able to buy a car, on a computer. I was like, what? How in the world? I didn't say it out loud, but my first thought was, how do you buy a car on a computer? You can't even test drive it. That's literally what I thought. It's like a really good lesson because I think I'm a pretty open-minded person. Like I'm very much, and it's not about politics, left or right. It's just that I could see things about how the future might be. For example, at the time I was at a military college, and the big debate was at that time it was all male. It's kind of a famous military college called the Citadel in in South Carolina. Has roots all the way back to the Civil War. Um, and the debate at the time is that, in fact, it was gender integration because the military was going through the gender integration. And how can you have a military college and you still like have the all male thing? It makes no sense, right? Because you're going to be going into so, but they were resistant because everybody, it's just human nature, I guess. I don't know. But I could see even then that was, it was silly. You gotta like, how you gonna any institution or anything as part of our country that doesn't change as the country change becomes archaic and useless. And so it's a no-brainer, man. You gotta let women in, right? Because you're gonna have women in the military. So, you have to, if this is the place that teaches you how to train and be a military officer, how are you gonna do that? And you don't even, and it's completely ridiculous, right? But I really didn't talk about it much because, people get into fistfights. We're getting into fistfights over the thing. Oh, but I guess the point I'm trying to make is that so much has changed since 1986 in so many different ways. And but even a forward-thinking person like me, like I think I am, my first thought was, how can, how you can't test drive a car? You can't even see the car. Like it's just because that's what happens, right? And this is just something for you as a scientist to be aware of. What I was doing, like there's something in quantum mechanics called the Heisenberg uncertainty principle. And I could talk about that for days, but it's one of the fundamental precepts of quantum mechanics. But one of the thing, and there's many perspectives you can talk about it, about the implications of it. But one of the things about the high that the Heisenberg's, well, what it states actually, and I'm generalizing here, is that like right in these equations we do up here, we assume that they are exact. We assume that when we make a measurement of momentum or velocity, whatever, we can do it exactly, and we do within. All you're always sending me these emails about, giving you back your credit from the way while it's taken off your points, and rightly so, because we're assuming that we can get an exact answer. But the fact is, we can't. It's not exact. It's just that the error is so small that it doesn't matter. That's why we didn't realize we needed something like the Heisenberg uncertainty principle until we started making instruments where we could measure the velocity and momentum and position of quantum or relativistic particles. Particles that were going very fast, a quarter of the speed of light, half the speed of light, and very small. Masses like protons on the order of 10 to the negative 10 to the negative 27, whereas my mass is on the order of 10 to the, you know, uh, what am I? I'm 80 kilograms, so that's 10 to the one, right? So that's a difference of, 10, that's a difference of 10 to the 28 in orders of magnitude. So that's what I mean. Like when you get down to masses that small that are going very fast, the errors that are inherent in these equations become huge. And so, really, these equations aren't correct. They're not exactly correct. They're just exact within our very large macroscopic world. So we don't, you don't have to. We didn't know that we had to know, relativistic mechanics and develop that. Quantum mechanics, actually, is what it is. So, as opposed to classical mechanics. Um, I lost my train of thought. But yeah, the point that I was trying to get to is that Heisenberg, yeah. So we'll talk about that in 39 if we get to, but just to throw it out, basically position and momentum, delta x, delta p, where p is velocity times mass. We say that there's an uncertainty that is always inherent. If you measure one, there's going to be an if you measure one to its exact position, then there's going to be an infinite uncertainty in momentum and vice versa. So you can only know the position and momentum of the object within a certain approximation. And that is the uncertainty. Now you want that uncertainty to be low, and you might be able to make some measure, but it's all relative, right? Because low just means if the uncertainty is low enough for whatever instrumentation that you're using. But there's always going to be some uncertainty. So you can either think about it in terms of energy and momentum or in terms of time and energy. You can write the Heisenberg uncertainty principle two different ways. Now, again, there's a bunch of stuff to get into it, but let me just break it down for you. Why there's an uncertainty there? It's not obvious when we're measuring something like a position, when we have macroscopic objects. But like right now, you can see that there's a light, a very strong light that I have for the board that's on me right now. I can cast a shadow onto the board. Well, if I were in a completely dark room where there were no light, you couldn't measure my position because you couldn't see me. So ultimately, in order to measure me, what do? You have to turn on the light. You have to turn on the light, and then you start with all the mechanics of your ruler, defining a reference frame, maybe the edge of this board, whatever. Then you measure my position. You assume it's exact. If you come up with the center of mass where you want to measure it from. And right now, it doesn't look like I'm moving. So you can say, oh, well, your velocity is zero. So I know exactly what your momentum is and what your. But the fact is, I'm not actually stationary. I'm actually moving. On a quantum level, I'm vibrating. Everything in me is vibrating. So the more you trace down to that, like if you wanted to see my center of mass, since my center of mass is, part of everything else on me that's vibrating, my center of mass is actually vibrating. And the closer you blow it up, the more that vibration is, right? If you want to get more and more precise, it's just, it's all over the place as you zoom in, essentially. So my momentum is not zero. And if I'm doing that, where's my position? Right? So that's kind of the explanation with a macroscopic particle. It's more obvious when it becomes a relativistic particle because with a relativistic, let's say it's a proton and it's moving, half the speed of light. So now it's in the relativistic realm. How do you measure the proton? You don't turn on the light and get a ruler. You measure it with light itself. Light itself becomes the thing that sees it and measures it, a light beam. You have a light beam. We just started collisions a while back. You have a light beam, photon hits the light beam, bounces off, and it tells where the proton was. But it's kind of like with magnetization, right? Like if you had a bar magnet, if I had a bar magnet on this desk right now, and I wanted to measure it where it was with another bar magnet, and I did that with a kind of a crude measurement. Can you see? I don't know if you can see with the other camera. Um, yeah, let's just go with that. In this camera, I want to leave it like that, but you can take a look at the other camera. So imagine, I don't have a bar magnet. Actually, I've got some circular magnets, but they're like, I don't know if I should use that. Yeah. So yeah, you know how magnets do, right? So here, let's just put the magnet on the table. So let's say that I have a magnet there and I have another magnet in my hand. I want to measure where the magnet is. And I'm just doing that by kind of sensing it. Now, if the thing is not magnetic, then like this is, I can kind of poke it and I can poke all around and find where the border, where it stops, right? And then I can map out a position like that. That's kind of what we do with light. Like the particle is moving along, you send light, it bounces off, send a bunch of different beams or whatever, and they all bounce off. And based because you know the initial conditions of the beam that you sent, wherever it bounces and reflects to, you can just take all that information and extrapolate where the collision happened. And so you can get an estimation for, where the particle was. But here's the problem. The problem is what's going to happen when I take this. I'm going to do something kind of like that with this magnet, get it close to it, and try to sense where it is, right? But look what happens whenever I do that. I'm starting to go to it. I'm getting close, and then bam. So now that's where the interaction took place. And that's not going to be the initial position because the fields of the two magnets interacted before they could even get in close proximity to physically touch. And so the field disturbed it from its initial position. And if you're talking about a proton, which basically is just going to be on a light beam or something, or even that's what light is, just a moving of, it's spinning, so it has a magnetic field. It's a wave, it's a particle, it can be both. We'll talk about that next semester. But the point is, like, it's light itself, and it has a field associated with it. Even if it were just a static charge spinning, it has an electric field and it has a magnetic field, as I've shown. Well, no, I keep forgetting this is not that class, but it does. So light, the photons coming, in the photon, it has energy in the field itself. So the fields interact before the particles can even get to one another. And so basically by making the measurement, there's no way that you can get around disturbing the original position and momentum of the particle by measuring the particle. It's inherent to the measurement process. That's actually very philosophical. I'll say something about that in a minute. That is the basis of the Heisenberg uncertainty principle. It means that it's why you need it, because on relativistic scale, you cannot make an exact measurement because making the measurement changes it inherently from what the original position was and momentum was in the first place. And because you can never get around it, you can only approximate where the original position and momentum of the object was based on the interaction that you get, namely that. So based on how that object hit my sensor, I can determine, assuming with certain assumptions, assuming that it started from rest, assuming that it was at a position, what the approximate position would be, or assuming, what its initial velocity and momentum were based on whatever it's in, whether maybe a beam of light or whatever. But it's only going to be an approximation because I can never really know for sure or by exactness because I always am going to change it as I get close to it. And here's the crux. If that's the true for a relativistic particle, and everything around us is made of relativistic particles, quantum particles just put together in more complex systems, how does it make sense that on a fundamental level, you cannot make an exact measurement, but somehow, when you put all those things together, you can make an exact measurement of the complex system that the quantum particles creates? That is illogical. I don't mean to sound like Spock, but that's just not even physics. That's just basic logic. That makes no sense. So it makes more sense then that even on a macroscopic scale, you're not actually making exact measurements. There is no such thing as an exact science. I know you heard that, but Werner Heisenberg, actually, he was in the movie, by the way. He was one of the characters in the movie they just did about Oppenheimer. But he was like the German equivalent of he had his lab. They showed it there a couple, I think, in the third act of the movie. But he was like the German equivalent of Oppenheimer over here. He was the person that the Germans recruited during World War II to create the bomb. Um, anyway, so that guy, Werner Heisenberg, he established this because they basically they had he is one of the constructors of the creators of quantum mechanics, um, which basically led to them being able to make the bomb. So basically, it was classical mechanics. I told you at between 1895 and basically 1910-ish, 1912, we realized all the stuff I'm telling you that just told you about because our instruments got better, you know, taking X-rays and stuff. And we realized when we started trying to apply these equations to spinning protons and electrons and stuff in theoretically in matter, we weren't getting the right answers. We're getting very wrong answers. So that's when people realized that maybe, you know, sounds blasphemous, but maybe Isaac Newton was wrong. Turns out he wasn't exactly wrong. He just wasn't all the way right. And who knows? He may have actually known it. Who knows about that dude? He did stuff and didn't even tell anybody. So he might have suspected maybe on some way that, you know, anticipating that maybe something could be different on a quantum level, but he had no way of proving it or showing it. But anyway, we figured it out by the turn of the 1900s, turn of the 20th century, the early 1900s. And so there were all these different experiments. We'll talk about this in 39, actually. All these different experiments that popped up that were verifying that classical mechanics wasn't completely right. So after a few years, a couple of physicists got together. Well, there were a lot, but there were three people driving it, driving the need. So by 1910, we realized we had to come up with a new science. And that science, whereas classical mechanics was Isaac Newton, they named it and it's mechanics, but it's basically the new mechanics or the mechanics of quantum particles, and they called it quantum mechanics. And so it took basically 20 years, maybe 25 years. So the official date is 1925. By 1925, Werner Heisenberg, uh, Max Schrodinger, and a French physicist, something Dirac, I forget his first name. Those three physicists um, are credited with basically creating quantum mechanics, the mechanics of relativistic particles. So, yeah, yeah. And yeah. Mm. Well, I hope you found that informative. Um, I think that's all I wanted to say. I kind of got off on various tangents there. But development of quantum mechanics and backtrack. So I was talking about uh, so no exactness. And forgot how I what started that. path of discussion. There's something kind of important I wanted to talk about. I guess I did say it. Yeah, so no exact science, position, momentum, Heisenberg uncertainty. So no exactness. Yeah, I think that was it. That was it. Yeah, but just that, it's illogical to think that, as I said, that if all of my quantum particles are moving around, then if you think of my center of mass, if you go to a large enough magnitude, it's moving around as well, right? Oh yeah, so I was going to kind of bring that full forward. I know there's one last point I wanted to make though. So that's a quantum level, right? Like you can't, and so therefore, even macroscopically, you have to understand that there's no such thing as an exact science. So when we're making these measurements, the presumption is that it's within the order, the tolerance of whatever the uncertainty of the measured values are that you're using. And but I think it also has philosophical implications, right? As philosophical. Thank you. Who's that? I just learned to do that the other day, actually. Uh, but it doesn't tell me who's actually doing the thumbs up. Can't really see it. But one thing I wanted to say to you about this that I thought about, years ago and kind of mentioned, it's this idea of like pure logic, right? That something doesn't come from nothing, or that if there's some aspect of something on a small scale, and then you create aspects of that thing with more complex systems with those small particles, even though it may not be obvious, some in some way that phenomenon has to then manifest holistically in that whole thing or some version of it. That's symmetry, right? So, I thought about these connections, maybe with what we might consider philosophy or maybe even, I guess, religion, but these certain precepts about how does that affect, how does that manifest on our everyday lives in terms of the way that we interact? Because everything is are quantum particles, not just these things that we isolate in our classroom and then talk about physical, but the definition of physics is that it's the study of the physical universe. So if you think about it, that is literally everything in the universe. Everything, energy, thought, matter, everything. Social interactions, all it's all physics. As that's the way I see it. Everything is physics. Everything. So I kind of explain it this way. And I don't know if physicists probably won't embrace this, but like many people don't, but whatever. People didn't embrace Galileo, didn't mean it was wrong, right? So the idea is that let's say that you're walking down the road, like you're on the side of the road, you had maybe you're down on Sunset Boulevard, Sunset Strip, you got a little cafe. And you see some dude walking down the road, and he's maybe a block away from you, and he's eating a candy bar. And he eats a candy bar and he's walking along and he throws a candy bar. He finishes the candy bar, but you know, he takes the wrapper and just throws it in the gutter, you know, litters. And, maybe 10 meters away was a trash can that he didn't see because maybe it was behind a pole. It doesn't matter. Like he could have put it in his pocket. Right. And so maybe this person, maybe you, I don't know, you're sitting at the cafe and you just happen to notice the guy walk and you see all of that, right? You see all of that before the guy even sees you, is even close to you. And you feel some type of way about it because, um, it's the earth, right? And you're polluting the earth. I mean, it was careless and needless. And it kind of rubs you the wrong way, right? But it's a free country, so whatever. Maybe you go pick it up after the guy walked. But the point is, in that moment, you see that and it gives you a reaction. And even before you have a chance to adjust or get it out, the guy is now there. And he kind of glances over and he's a happy-go-lucky guy. And he looks at you and he speaks. Hi, how are you? Just because you guys met eyes. But then you're in your mode. It's kind of you didn't really expect it. You're still thinking about the fact that, and so you don't realize, but you kind of giving off an attitude, right? And you don't even know how you feel about the guy. You don't really want to speak. You're pissed. Should you say something? I don't know. Then you say, well, it's just maybe it's easier for me to just let this dude go on by, and I'll pick up the thing when I leave or something. I don't know. But the point is, you don't give him back his happy-go-lucky high, right? You just say, something like that, and then you just continue on. Don't you hardly pay him attention. Now that's all he knows. He sees that, he says, and then that gives him a certain kind of way, right? He continues walking, there's no interaction or whatever, but he forms an opinion about you. It's a judgment, it's a measurement. Any judgment is a measurement. Energies interacted before they even were in contact with one another based on the actions of those energies. They are mutually responding to one another because now he walks away and he says, "Oh man, that guy's he's having a bad day, or he's kind of a not a very nice guy." I wasn't doing anything. I spoke to him. I was very happy. I was very nice. He's just giving that attitude, you know. And now he's making some subjective judgment about not even realizing that he's actually in some way getting back a reflection of what he put out, and he never even knows it. And now I don't know. Like I sometimes I make the say the story better, but maybe with the reason he threw the thing in the gutter was I don't know. Maybe it's something. Maybe he's not normally a literate person, and maybe he actually is big door. But I don't know. Maybe he had a lapse or something. I don't know. That's I can't. I'm have maybe make up a better story to say like why he accidentally. Maybe it fell out of his pocket and he didn't see it or something. Or he tried to put it in his pocket and he missed and didn't pay attention and you didn't really see that he tried to do that. All you just looked like the he was eating the candy bar and then you looked away and the next time the candy bar is flying behind him on the gutter. So maybe he didn't even mean to litter, right? He thought he still had the thing in his pocket. Something like that, right? Where people are making judgments and they don't have all the information. But a measurement is a measurement, right? So that is a way that maybe I might say how the Heisenberg uncertainty principle might, on some macroscopic level, be kind of, filtering through to these more complex systems, right? Because no measurement is actually true. It's only an approximation. Because if you can't do it on the quantum level and no measurement, no kind of, that's what quantum mechanics says. No measurement at all. Position, momentum, energy, or time, which means that there's nothing that we can do. That's how I interpret it. The tests I give you, meeting people, making judge, all these things, because the basic definition of a measurement is just the interaction of energy, because everything is energy, right? So, you know, when you meet someone and you are interacting with them, it's a measurement, whether you consciously realize that or not. You're going to make judgments about the person, good or bad, ugly, whatever. So if I mean, I just think about if everybody knew physics and really catered to physics, what that would actually do. If we understood that no matter how right we think we are with regard to assessing a circumstance or situation or people or person, there is no way that we could be absolutely correct. None. And that's fundamentally associated with our universe. Just maybe we might be a little bit more open minded when we deal with one another. If everybody really understood basically what science seems to say is how our universe works and how it's made. So that's a precursor, and maybe a little bit of a commercial advertisement for taking my Physics 39 class, if you have to take it at some point, because later on, in the class, the latter portion of class, we'll start to get into some of those things and look at some of those principles. But yeah, yeah. So vibration, is it's really ultimately the only kind of motion there is really. I'm breaking up into these classifications of motion, culminating with the eighth type being oscillatory motion. But in fact, the only kind of motion there is oscillatory motion. All these other motions, constant velocity, constant acceleration, they're just kind of zooming in or zooming out, that is, so that uh, something looks like it's not moving very fast or moving at all. Yeah. All right. Which time I got? 20 minutes? 20? No, 30. So it's 403. So I got about 30 minutes. Well, let me just do this next section where I just, and then also energy, and that'll probably finish. That'll be half the chapter. And I won't get into moment of inertia. I have to wait till I need a whole fresh class to do that, I think, and introduce it. But yeah, so any questions, comments, troubles, gripes, about what I've been talking about here? Just kind of a break in the semester where I like to kind of tighten it up. We're about to, kind of do a, we're about to jump off and do some different things that certain kinds of quantities we haven't, they're not analogous to what we experience in, well, rotational. And we still got to go back and get those, got to put that. Now we're going to be able to go back and put the pulley stuff in and do some of those same problems we did with blocks on planes, but not put the pulley in. I mean, we have to get to the next chapter to do that, but you get that information, but we will do it. So let me go ahead and get this done. So yeah. Um, well, the first equation I've already written here is the equation that relates tangential velocity to angular acceleration. Um, and actually, I guess I've already done both of them because we used. Yeah. Mm. So to reiterate, so this is section is called linear what? Relationship between rotational and translational quantities. Um, well, we already showed that the translational speed is equal to r times the rotational speed, the angular speed, angular velocity, well, speed, because we're not writing the vector form of the equation. And yeah, and if we take the derivative again, we get that similar relationship between linear acceleration and angular acceleration. Just taking the derivative, we get that. Well, why don't I just do it? So what, 25, 24. So taking the derivative of this guy, and remember, it's like, so d dt of v of t equals d dt of the quantity r omega z. But that's the product rule, right? So this is just the derivative. So this is just becomes the derivative of velocity becomes tangential acceleration. And so this becomes r d omega z dt plus omega z dr dt. Now the r can change. That's more advanced physics, more junior level physics, and then we can work out equations of motion with those. But when the r is constant, like it was assumed to be in this case, that term is zero. And then this becomes just a of t is equal to r times alpha, because that's just alpha z. So the simple version for these two are this guy, this guy, but we're not done. Gonna bring back something that we've already studied. Remember, that's the tangential acceleration, but it can have a radial or a centripetal acceleration. Centripetal acceleration is defined as AC is equal to v squared over r. But if v is equal to, and this is the tangential speed, right? If that tangential speed is equal to r omega, when I put that in, I've got r squared omega z squared over r, when the r's cancels. So I have centripetal acceleration also can be written in terms of rotational quantities just as well as uh, tangential or linear acceleration. Remember, tangential and linear are the same. And the tangential, points, as I said, tangent to the path, but the centripetal, points always perpendicular to the velocity toward the center of whatever that curved path is. If it's a circle, it's the center of the circle. So the tangential acceleration, AC, 29, AC is equal to, it's going to be R omega Z squared. So that's kind of a change there, right? The tangential acceleration is proportional to angular acceleration and the proportionality constant being r. The centripetal acceleration is proportional to the square of the angular speed, and the proportionality constant is the radius. Actually, it's not really, it's only a proportionality constant in this case where the radius is constant. But in general, maybe that's not a way to say it because it's going to be a bit more complex. So we can then write the total acceleration then, right? Just common sense and definition, Pythagorean theorem states that, if you have something moving in a curved path, I've taught you this, right? A curved path, where that's the tangential speed v. If the speed is changing, so, well, that's the direction of the velocity, but at any point, the tangential speed is going to be tangent to the path, as I've just been repeating over and over. So that's v, but it's going to have, a acceleration component, like say if it's speeding up, it'll have an a t, either parallel or antiparallel to the velocity, but it also has an AC or AR, it might be a radial in your book, but I'll call it AC because that's what we've been calling it. That's along the perpendicular to the velocity. And remember we said that's actually if it's a circle. in general, it won't. Well, yeah. Sorry, the centripetal acceleration is always perpendicular. So the total acceleration then is going to, in this case, it's going to be at some. You can kind of sketch it out using the parallelogram method. That the total acceleration it's not along. It's making some angle phi relative to. I think I called it relative to velocity when we studied it back in um, you know several weeks ago. And so this angle phi, whenever the velocity is increasing along a curved path, then phi is going to be greater than 90 degrees. Whenever there's no acceleration, then this term is zero, and the total acceleration is equal to the centripetal acceleration. In that case, phi is going to be 90 degrees. And whenever the object is slowing down on a curved path, the tangential acceleration is opposite direction of velocity, which means the actual total acceleration, since centripetal is always perpendicular to the velocity toward the center of the curved path, then that would bring the acceleration back in the opposite direction, in which case phi would be obtuse. So phi is acute, less than 90 degrees when it's accelerating, obtuse when it's decelerating, and perpendicular because it's also equal to AC whenever there is no acceleration along a curved path. So that's now consistent with things that we had talked about, months, at least weeks ago, over a month ago, I think. But for this particular example, if the acceleration is increasing on a curved path, that's what it would look like. But the point is that these are just the components of the acceleration. When you throw in rotational motion, you can now write acceleration as having two different components, one tangential, one radial. Radial meaning perpendicular to the velocity. So that the total acceleration, A vector, is equal to A centripetal vector plus A tangential vector. I can do the Pythagorean theorem to get the magnitude, right? A dot A, right? A dot A is going to equal to A squared. So that's going to be equal to basically AC squared plus A T squared, the magnitudes, so that I can say that the magnitude of A is equal to the square root of AC squared plus A T squared. And if I then put in these values here, I can write that in terms of circular motion. So what are we doing? So yeah. So this guy is R, so AC is equal to R omega Z quantity squared plus AT is R alpha. So R alpha Z quantity squared, all of that to the 1/2 power. And then simplifying even further, we will get that AC is equal to, well, I can have an R squared and omega squared. The R squared can come out. I guess it could. Sure, why not? I take it. So R squared to square root will be an R on the outside. And then in brackets, I'm going to have omega Z squared plus alpha Z squared to the 1/2. Something's not right. Is that right? No, because this was already squared. Yeah, this was already squared. So that should have been a squared inside there. So now this is to the 4th. There you go. There you go. That's it. So that gives you the relationship of acceleration, velocity, and displacement. Remember, the displacement position is just the uh, the equation for, I forget the name of it. The arc length formula for position. Mhm. Any questions? Gotta speak back. Okay. Yeah. We're trudging along here. Let's take a look at energy for rotational bodies. Kinetic energy. Oof. There is a work energy theorem for kinetic energy, for energy in general for these guys. So I need to, the ink is getting low. Finish some of these real quick. I want to perform, when I'm finishing this ink, let me perform a thought experiment. So keep the momentum going here. And ask you a question about something, see how you respond, you think about it. Will this roll? Yeah. Okay. I should be careful with these magnets. I've actually erased a computer from my lap. It was old, but I erased it prematurely. So let's take a look at this guy. You got this thing rolling down here, or this is kind of small. Let me take this out of here. Get a bigger ball. I got a piece of tape ball that I made for this purpose. Oof. Tape ball. Where's my tape ball? Right here. Okay. Think about this. Come over here so you can see it well. Make it flat for you in front of you. Actually, I do. Uh, you know what? I need two objects though, don't I? So let's say, I think I have some here in my little box. I have something set up for this. Yeah, these two. Let's do. Oh, here we go. There you go. Yeah. I have two objects here. They're the same mass. They're basically little tape things. They're like the dispenser tape inserts thing that you put the tape on. I don't know why I say these. They just look like little things I could use in making physics class somehow. Well, and I'm using it, aren't I? So maybe. Uh, let's say that we have one. So we know what kinetic energy. We defined it already, right? Did we do it? Yeah, we did that last couple chapters ago. So kinetic energy is defined as 1/2 mv squared. So it has a mass. I don't. I probably wouldn't show up. The mass is probably like 7 grams or something like that. But anyway, oh, I'm sorry. Yeah, maybe. Um, might even be not. Yeah, no, probably wasn't even a gram. Actually, I'm gonna go measure it real quick. I'm curious. Trying to get my order of magnitude on this thing. Intuition for what a gram is. Uh, huh, it's 3 grams. Okay. That helps guide the intuition, 3 grams. Now, we know that by definition, the formula for kinetic energy, energy of motion, that's literally the definition. Kina is Latin for motion, and tic is like an adjective, is just whatever, you get it. So K is 1/2 mv squared. Translational speed. Now, these things can roll. So if I roll it along, it's so obvious. So energy of motion. We're just now classifying rotation as a different type of motion, right? So like if I were to take this and somehow hinge it, if I had like put spokes in it or something and I hinged it and I twirled it, spun it, or maybe put it on a tabletop and spun it, or even maybe if I spun it like this, like in that, basically, but it's not, but its center of mass is not actually translating. Well, does it have kinetic energy if it's doing that? Well, if kinetic energy is just energy of motion, and even though it doesn't have any linear motion, it's got rotational motion, omega, it's got motion. So it should have some kinetic energy, right? Obviously, if it's translating along, if I flick it along like a hockey puck on a glass surface or a slippery surface and it slides along, well, it has linear velocity, so clearly it does have kinetic energy in both of those separate cases. So maybe I pin it with spokes or something, I spin it and it's spinning in place, it has kinetic energy. If I don't spin it but slide it along, so it just has linear motion, it has kinetic energy. But my question to you is this: what happens if it does both? If by rolling it, I give it both linear motion and translational motion? Does it have more energy than it would have if it were just doing one or the other? In other words, let's say that I take a mass that has equal mass, and one I allow it to roll along, but the other I just kind of hold beside it with the same speed at every point that it's moving. Which one has more kinetic energy? The one that's rolling, or the one that is translating beside it without rolling, or do they both have the same kinetic energy? Now, I want everyone in class to respond. So I'm going to call on you, and I want you to vote. Either way, like however you want to do it. So I want to see you too. I can't see everybody right now. So we just have testing. Okay, we're back. So Armand, which one has more kinetic energy? The one that's rolling, or the one that's just translating, or the one that's rolling and translating? Ratch, what about you? Are you there?
I suppose it's the one that's rolling and translating.
Okay. Aaliyah, do you agree or disagree? All right, maybe Ratch, we'll just go with that. Well, yeah, that's a good answer. I would agree. And what's your logic in that, Ratch? What's your justification?
Well, my like the reason why I'd say that it have a higher kinetic energy when it's rolling and translating is because like whenever an object is strolling, it has rotational kinetic energy, right? Like
Hmm.
that's just in like one form that it's getting kinetic energy from. But whenever it's translating as well, there may be like another action that's being put upon it that's causing more kinetic energy to be created. That's the way I'd like look at it in my head.
That's an awesome way to look at it, Ratch. Well done. Yeah. Because translational motion and rotational motion, they can come from two different types of external influences, two different types of forces. In other words, energy doesn't change. So, and whenever I give something, we saw previously that there's a connection between work and a change in kinetic energy. In fact, it's just that simple. Work equals a change in kinetic energy. So if what you were trying to say, and you pretty much said it, what causes work? Well, it's a force, you know, the mechanical work is F dot dx. So you're applying some kind of force that might be making it rotate, or it might be making it translate, or maybe it's doing both, but those are two different types of motion. So there must be enough force to do that. And there you can think of them as separate types of forces because they're giving rise to separate type of motion. Just in the same way, we thought about in kinematics where parabolic motion is motion in one direction and combined with motion in the other. And they're separate motion. And there can be forces, different types of forces in either direction causing those different motions. Gravity causes it to go down, but some sort of force, either pushes it along in the x direction. In terms of parabolic motion, there is no force in that, but there could be. There could be drag that kind of truncates the parabola. So in that case, you've got two different things going on in two different directions, giving rise to two different types of motion that when you combine them, it gives the resulting parabolic or whatever it is. Now, this is not a vector. Energy is not a vector, right? When you do work, that's energy going in, but you can have different types of energy because it's giving rise to different types of motion because of different types of forces doing work. There can be more than one force doing work. So that's a wonderful way to think about that. And I applaud that. Yeah, good, good. So let's prove that. Let's prove that if something is rolling along with a mass that's equal to something that's translating beside it with the same linear speed, that the one that's basically rolling and spinning has more kinetic energy because it would have had to have had more work done on it to take it from rest to give it those two different types of energy. When we get to upper level physics, we get into something called degrees of freedom. Degrees of freedom. And you can have different forces acting along the different on an object to give it basically different types of motion along its different degrees of freedom. And anyway, that's a different discussion because it basically gives a top limit on the amount of mechanical energy that you can give something, depending upon, well, in terms of motional energy, which you can then describe in terms of heat and things with kinetic theory. But that's again, that's physics 39. But yeah, so let's just take this definition here. And now since we have this guy, we can substitute that into here to show basically this is considered translational kinetic energy. K trans is this guy. But what is rotational kinetic? K rot. I'm just using that as a, what does that look like? Well, if I take equation, whatever that was, and stick it in here, and I'm going to keep the numbering going, I guess, because 35, call this 36, 37, 38, and taking, it looks like that was 24, and putting it into 36, I'm going to have 1/2 m times r omega z, but that quantity is squared. And so K rot then is equal to 1/2 m r squared omega squared. Now, this quantity here, I have to do something I have to give you some more information here. This quantity is a thing. It is something called moment of inertia. So I have to define that here. It comes out of the derivation of rotational kinetic energy. So 39. So I'm going to say that moment of inertia, not moment to be confused with moment arm, something else, that's with torque, but moment of inertia. And whenever people use the term moment independently without like beginning qualification, they're usually talking about moment of inertia. But it can be confused with uh, moment arm. Sometimes people also mean moment arm too, I think. Actually, you know what? You just have to, I never say one without completely qualifying. Moment arm or moment of inertia. Moment of inertia is defined as basically mr squared. But the fact is, there's a numerical value out here. So I'm going to put 1 in parentheses, mr squared. That's the mathematical definition. But this constant can change based on certain properties, or one basic property, and I'll talk about that right now. So let's first define moment of inertia. Oh, I thought I was gonna. Yeah, I'm sorry. I got on the. I was gonna, but because you got it, you got it so fast. Usually there's a little bit of debate because I was gonna put in my ink while you were debating whether or not what what and what has more kinetic energy. But usually, you did. It was no debate because you nailed it. So I got to do my ink then. Um, yeah. So this is what we have to talk about on Monday, but let me introduce it right now. Moment of inertia. Now you remember how much time I got? Oh, wait, what? How did it get 434 so quickly? I thought it was just 403. Oh, I'm so sorry. Uh, and I guess you're gone. Yeah. So okay. Let me wrap this up then. Yeah. So moment of inertia, and so I can write the kinetic energy in terms of moment of inertia, and then it just becomes. Well, I guess I did all that stuff. So yeah, I guess I did use up the 30 minutes. If I take equation 40 and stick it into this thing, then I have that kinetic energy for rotational motion, k rot, is equal to 1/2 I moment of inertia times angular velocity squared. So that's rotational kinetic energy, and translational kinetic energy is the conventional standard 1/2 mv squared. So 1/2 mv squared versus 1/2 I omega squared. So the thing that's rotating and translating has 1/2 I omega squared and 1/2 omega squared. The thing that's 1/2 mv squared. The thing that's translating just has 1/2 mv squared. So we could then put these two together, right? K total is equal to K rot plus K trans. And so that's going to be 1/2 mv squared plus, putting the stuff back in, 1/2 I is mr squared, omega squared is v squared over r squared, because v is r times omega. So the r squareds go out, and I basically have 1/2 mv squared plus 1/2 mv squared, which is just mv squared. So for something that is rotating and translating, the total kinetic energy is mv squared. So it's twice as much kinetic energy as if it were, um, you know, if it were just translating. It has twice as much energy if it's rotating, um, like rolling along, such that it's translation. The translational speeds are the same. So if the translational speeds are the same, then the one that's rolling will have will have twice as much kinetic energy. Interestingly enough, one last thing I'll say about that: when something is rolling, it is essentially tripping up on itself. So you could make the argument that because of friction, you can make the argument that torque is doing work on the system and torque is doing a positive work on the system. But the torque is coming from friction, static frictional force. So you can kind of say that it's a circumstance in which friction actually can put energy into a system as opposed to taking energy out of the system by applying a torque to it, as long as there's no slippage. And so as long as it doesn't cause, well, it's static friction, but it's not kinetic friction. So the static frictional force uh, causes a torque that basically increases the energy of the system, as opposed to if it were sliding along at a frictionless surface and with the same speed. But yeah, we'll talk about that next week. All right. Well, class dismissed. Yeah, I think this was a good class. We made some traction. And this is chapter 10, and we're about two-thirds of the way through. Go ahead and take a look at that because we're going to get on to chapter 11 by next Monday. All right.